Okay, today let's continue with logarithm and exponential. So let's say general log and exponential functions. So let's start with the warm-up exercise. So the first thing is to show that e to the x plus x equals 0 has a solution. Okay, so we have methods, numerical methods to check the value of these solutions, but first you have to make sure that there is a solution. You must have an idea about where the solution is, so you start your numerical methods around that point. So first you draw a graph. First sketch a graph for y equals e to the x. And you see this is e to the, you are looking at when e to the x is equal to minus x. So you look at the graphs of these things and check if they intersect. Okay, so for this one we use the general knowledge that the graph of this comes from almost 0. Okay, as x goes to minus infinity, this is asymptotic to 0. So it is something like this. We know that this grows very fast, but we are just drawing something symbolic. So this point is 1. Y equals minus x is this line. Okay, so it passes through the origin. This is y equals minus x. Okay, so you see this graph is below y equals 1. So if we consider this box, this is minus 1, and this point here is minus 1, 1. There's a solution, there has to be a solution in between. Okay? So using this, we can now convince, this is the information you receive from the graph, but by experience we know that graphs can be misleading. Why is this graph correct? So we have to convince ourselves that this is correct. What we use here now technically corresponds to intermediate value theorem. Okay, so that's what we have to find some values now. Okay, now calculus. Okay, so we consider the function, we consider this function, f of x equals e to the x plus x. Okay, we check minus 1. Okay, f of minus 1 is 1 over e minus 1. Okay, and this is less than 0 since e is larger than 2.7, okay, and 1 over e is less than 1. Okay, so this is negative. Okay, so what we did is we convinced ourselves that at this point, you see, I subtracted this number from this number, so this is the difference I find there. Okay, so I verified what I see in the picture there, and then I do the same thing here. F of 0 is equal to e to the 0 is 1, so this is positive. Okay, so this plus this is 0. Okay. Okay, now this is intermediate value theorem confirms that they intersect. When I take the difference will be 0 somewhere in between. So by the intermediate value theorem, there is some number x sub 0 between this point and this point. Okay, so minus 1, 0. Okay, such that f of x sub 0 is equal to 0. Okay? So in my picture now, it corresponds to this point. Okay, so the next thing is to find an approximation for this point. Okay, so we are expecting that x0 will be some value between -1 and 0. So one method that comes to mind is to use Newton's method. Okay, so maybe I use, okay, let's write this here. To find an approximation for x sub 0, we can use Newton's method. Okay, so there are other methods, of course, but in calculus we solve Newton's method. So for Newton's method, now I'm not using that graph, I am using this graph. Okay, so if you look at that graph, so y equals e to the x plus x looks like something like this. Okay, so if I have, if this is, so it's the picture here is something like this. Okay, it passes through here again. Okay, so it will be like this. Okay, so x, and this is my point, x sub 0. Okay, so Newton's method means that start from some point here, go to the curve, draw the tangent and find the intersection point of the tangent and repeat this. So you see that the figure convinces us that we will approach to the root, and technically we know that if it approaches to some point, it's the root. In this picture, we are convinced that there is only one root. Okay, so this curve doesn't come back and intersect this anywhere else. So we'll use Newton's method. Okay, so Newton's method, let's remember what it was. Newton is not what we have in mind. Newton's method for y equals f of x is, you consider a sequence xn minus f of xn divided by f prime xn. Okay, you start with a guess, and then this is the x-coordinate of the point where the tangent line at this point intersects x-axis. Okay, so this also you check that if f prime is 0, the tangent line is horizontal, and the tangent line will never intersect x-axis. So that's also read from here. Okay, so for this, so we use f of x equals e to the x plus x. So when we write this, so in our case, then xn plus 1. So I simplified these things. Okay, so you take the derivative of this, put it here. So what you get is xn plus 1 is e to the xn times xn minus 1 over e to the xn plus 1. Okay. Now we have to start this from somewhere. Of course, you try to make an educated guess. In the picture, it looks like as if it is in the middle. It's probably not in the middle, but we have to start from somewhere. Okay. Start with x sub 0 equals minus 0.5 from the figure. Okay. So if you do this, then x5 equals x6 up to 2, 4, 6, 8, 10, up to 10 digits. Okay, and that's equal to minus 0.5671432901004. Okay, nobody uses this much precision, but we are interested in this much. So it's slightly to the left of the middle point. Okay, so that's how in practice, that's how you use Newton's method. If you know that there is a solution there, and this thing starts giving you the same number up to the precision of the software you are using there, okay? So you take your chance and you say this is the root. Okay, so this is what we do with the, you see here we use two different things from calculus. So let us use another thing which, okay, so later on we'll have other methods of doing this, but this function, approximate integral from 0 to 1 e to the x square dx. Okay, so the idea here is to again demonstrate our methods. Next semester, when we start with Taylor series, we'll see that using Taylor expansion, we have another method to find an approximation for this. So here we will use, consider the function f of x equals e to the x minus x minus 1. Okay, so f of 0 is 0. F prime x is equal to e to the x minus 1. So this is always 0 if x is positive. Since e to the 0 is 0, okay, and after that this is large, so this is always positive. So what does this say? This says that the function is increasing. So f is increasing on 0, 1. Well, we are interested on 0, 1. It is increasing up to infinity, but we are interested on 0, 1. Okay. So we have so this is increasing, so 1 plus x is less than e to the x. Okay, let's write less than or equal to, because we'll talk about we'll talk about approximation, so we are not interested in precise sharp inequalities. So this is less than or equal to e on 0, 1. Okay. On 0, 1, x is less than 1, so this is less than this. Now put x squared for x. Since x is between 0 and 1, x squared is also between 0 and 1. Okay, so that's what we watch. So 1 plus x squared is less than or equal to e to the x squared, still less than or equal to e on 0, 1. Okay, now we can take integrals of both sides, well, 3 sides. Okay, this gives integral from 0 to 1, 1 plus x squared dx less than or equal to integral 0, 1 e to the x squared dx less than integral 0, 1 e dx. Okay, so this part is e. This part is x plus 1 over 3 x cubed, okay, from 0 to 1. Okay, and then when you put in the numbers, this is 4 over 3. Okay, so we found 4 over 3 less than or equal to 0, 1 e to the x squared dx less than or equal to e. Okay, but this encourages us to go further, because you see this is just 1.3 1.33. This is 2 point something, 2.718281828, etc. Okay, so we can maybe imitate this process a little bit more. Instead of approximating this by a linear term, maybe we approximate this by a quadratic. If I have a quadratic here, you see it will add a few more terms here, and this number, the number I find on this side, will approach up, and then it will squeeze this into a interval, and I'll get a better approximation. So let's try one more approximation. Okay, so let me see what I did here. Okay, so encourage with this. With this. Try f of x equals e to the x minus 1 minus x squared over 2. X squared over 2. So next semester we'll see that the functions, the polynomial I want to write here is the Taylor polynomial of this. So I'm not just making this up. Okay, so but at this point, let's consider this just a miracle. We sleep and we wake up and we say, why don't we subtract x squared over 2 from this? Okay. On 0, 1. Okay, so the same things hold. Okay, so you see that f prime x is equal to e to the x 0 minus 1 minus x. Okay, so that's the advantage. But we just found that this is positive on 0, 1. Okay, so this was that was the function we found here. We found that its derivative is positive, so this is always increasing. Okay, but it starts at 0. If it is increasing, it's always positive. Okay, so it shows us that this is always positive. But when this is positive, it tells me that this is increasing. Okay, so this tells us that f is increasing. Clearly, f of 0 is 0. Okay, so these are 0. This is 1 minus 1 is 0. So f of x is positive. Well, okay, 0 at one endpoint on. So let me say 0, strictly positive on 0, 1. Okay. So that means now I am imitating here. Okay, so now I am at this stage. So 1 plus x squared over 2 is less than or equal to e to the x less than or equal to e on 0, 1. Now put x squared for x. 1 plus x squared plus x to the 4 over 2 less than or equal to this, less than or equal to e. Integrate. Integral from 0 to 1, 1 plus x squared plus x to the 4 over 2 dx is less than or equal to e to the x squared dx from 0 to 1. Okay, so this is e. On this side, let's see what we are having. We have x plus x cubed over 3 plus x5, 5 times 2 from 0 to 1. Okay, so when we write this thing, let's see, I have 1 plus 1 over 3 plus 1 over 10. Okay, so, and the result is 43 over 30, and this is approximately 1.43. Okay, so I got a better approximation for this. So in fact, we can repeat this as much as we like, okay? So because you see, this tells me what will happen in the next step. I want to add here something so that when I take its derivative, I'll get minus x squared over 2 here, okay? So, and then I will know from this stage that it is always positive. So it will tell me that the new thing here with the added thing is still positive. So if I subtract x cubed over 3 factorial, okay, when I take the derivative, 3 becomes 2. And then when I put 3 here and I have 3 factorial here, 2 will survive. So I'll have minus x squared over 2 as I intended. So the next thing, I'll have x to the 4 over 4 factorial. So I can do this all the time. And then I'll put x squared for x. I'll integrate. So it doesn't matter what I have in here. I'll have just once. So all I have to do is to understand these numbers. Okay. So when you do that, you get this thing after you integrate. So if you add up summation k equals 0 to some big N, 1 over, so I'm writing just this part now, 1 over, you see first I have these, this is 1, this is 3, this is 5, so I have these numbers here, okay, 2k plus 1, those odd numbers, and this is 2 factorial here, and then I said I'll have 3 factorial, okay, and when I integrate that, all even number will be increased by 1 and will be put in the denominator. This is the even number increased by 1 and put in the denominator. And here I have the factorial. The factorial is k factorial. Okay, so this is what I obtain at this stage. So this number is always less than or equal to 0, 1 e to the x squared dx. And this number is always less than, well, strictly less than e anyway. Okay, let's put this, because every time you say something is strictly less than, then you have to prove that they are never going to be equal. We don't want to do that extra work. We don't need that. Okay, so here for n equals 20, you get 1.4626, etc. Okay, so 20 digit. It turns out that this 20 and this 20 is the same 20 digit approximation. Again, the method here I'm using is ad hoc. I start adding these terms one after the other, and I watch what's happening on the screen, and after a while you see the same numbers on the screen. So whatever is happening on the right. It will never, you believe that it will never affect it. There is a way to check that what happens after the 20th digit will never accumulate to anything on this part. Okay, but we'll do these things next semester. So at this point, I just believe that if the first 20 digits are the same from some point on, that's the answer. Okay, so this is actually the answer for this thing. So we started with an approximation, but numerically we found a precise value for this integral up to a certain digit. Okay, so you see that all the methods we used, except the religious belief here, is everything we did in calculus. Okay, any questions on these? No, you totally understand and enjoy everything we are doing? You don't enjoy these things? Okay, so what question do you have here? The only question you may have at this point is, how do you conjure up these things? Okay, so the answer is you play around. Okay, you make lots of mistakes. You start playing with this equation. You make lots of mistakes, wrong attempts, and eventually something starts to emerge. Then you hide all your mistakes and you just talk about the correct things you did. Okay, so yes, another question.
How you can put x squared instead of
How did?
you
Okay, so let's take, for example, let's take this one. For x, so this means on this one means that x is here. Okay, so that is for x in 0, 1. Okay, so how do you read this? For any value between 0 and 1, if I put here instead of x, that value, the inequality will hold. Okay, because this inequality, this is a function of x. Okay, if I put 0.5, this inequality will hold. Okay, so when we say that this inequality holds on here, so whichever value I choose from here and put here, I get these three numbers in this order. Okay, when x is here, x squared is also here. Okay, if this was instead of 0, 1, if this was between 0 and 2, then I cannot put x squared instead of x, because when x is larger than 1, x squared may be probably 3 or 4, it will be outside the interval. Okay, so that's the trick we are using. Okay, so the only question that may be in your mind is how do you come up with these tricks? That's after you solve lots of problems, you develop this repertoire of tricks. That's why you should try the exercise at the end of the book. No matter how routine they are, if you solve lots of exercises, then you say, okay, now I can solve everything. That's wrong, but the feeling is correct. Okay, that should be your attitude. Okay, other questions? Okay, so let's start with something else. So this logarithm is called the natural logarithm. The base e is somehow considered to be the natural logarithm because it's given by the area under 1 over x. Surprisingly, the area under 1 over x mimics all the properties of a logarithm function. So that's why we say let this logarithm be the natural logarithm. But once you start expressing the natural logarithm and its inverse exponential as e to the power something, you say, why don't I take nicer looking numbers and use them as base? Okay, that's possible. Okay, so general log and x exponential. Okay. So if b is positive, b is a positive real number. B is for base, to remind us what base is. Okay. And r is any rational number. Okay. We showed that b to the power r is well defined, and it is equal to, now we use the natural number, e to the r log b. Okay, so this is why we need, b positive in calculus. Okay, so in complex calculus, this equation is also true. The only thing you want is you don't want b to be 0 because log 0 is not defined. It doesn't make sense whether you use complexes or non-complexes. But for complex numbers, logarithm of everything exists. So for complex calculus, all you need is b different than 0, then you have such an equation. Okay? But in calculus, we are trying to understand what happens on the real line, and then logarithm is defined only for positive numbers, so we need it here. Okay, now if this is true for all rational numbers, we look at this equation. This equation at this side makes sense no matter what r is. Okay, so that's the bridge jumping from rational numbers to all real numbers. I try to make sense of this. You can take powers of this, you can take roots of this. So that means here you can put a rational number. Okay, so m over n. M takes powers, n takes roots. That makes sense. But when it is equal to this side, you see that I can take the logarithm of this positive number. I can multiply it with any real number. This exponential is a function whose domain is all of the real numbers, because I defined, that was the reason why we defined the natural exponential function as the inverse of the logarithm function. Okay, so it doesn't, we don't define it as e to the something, because then we still have the same problem here. What do you mean by e to the something? Okay, we defined it as the inverse of the logarithm function. Logarithm function is defined as the area under the curve, and area under the curve is defined by Riemann sum, so everything fits together, there is no gap. Okay, since exponential function now takes accepts all real numbers, here there's no reason to check that this is rational or not, because this is not going to be rational anyway. Okay, so we extend b to the r for all r in reals as b to the r equals e to the r log b. Okay, so we call this part, this is now exponential with respect to the base b. Okay, so for example, you can look at funny numbers like this. Okay, so what does this mean? This means that you look at e to the square root 3 times log pi. When we write log pi here, this is ln. Okay, so I'm using log ln as notation. So later on, sometimes we use ln only for reals. This is for everything, but after a while you say, I understand from the context what is going on, so you can use log for everything. Just make sure that you understand the correct thing. Okay, so this number turns out, well, incidentally, this number is, I had time to calculate these things. And this is approximately 7.2625 something. Okay, so rules are the usual ones. I'm not going to prove these things, but technically in the book you have to prove this, showing that, remember, everything started with Riemann sums and we come up to here. So you have all the reason to suspect that maybe something will go wrong. So you have to check all of these rules. It turns out that nothing goes wrong because everything naturally fits together. So we have, somehow I shifted from, okay, so I have A, B, positive numbers. So these are going to be bases. And I have X, Y, any real numbers. So here I will use A, B for this one, X, Y for this one. Okay. So the usual rules are a to the x plus y is equal to, okay, just let me do one of them, e to the x plus y times log a. Okay, so this is e to the x log a plus y log a. Now for the property of this one, I can write this as x log a times e to the y log a. Now I again use this formula. This is a to the x, a to the y. Okay, so we were expecting this. So you see that last time we proved the rule for the natural one, so everything else follows from the properties of the natural one. So the others are easy. X minus y is a to the x, a to the y. So you do the same thing. And a x y is a x y. So again, you are multiplying these things. And a b x is a x b x, as we expect from such things. Okay. So let's see what we have. Okay, so we have times. So let's look at graphs of these things in general. Okay, so you see b base number for this exponential function is anything positive. Obviously, it will make a difference if b is less than 1 or larger than 1. Let's see what difference will it cause. Graph of f of x equals b to the x. Okay, so here b is positive and x is any real number. B, this is fixed, of course, and this is my variable. I know that this is defined in this way. Okay, so f of x is equal to b to the x. This is e to the x log b. Okay. In order to understand the graph, our main tool is to look at the derivative. The derivative tells us how fast this function is increasing or how fast it is decreasing. Okay. So f prime x is equal to, well, I don't know how to take the derivative of this, but this is what I know. I know the derivative of this. Exponential of something is, first of all, that's something. So I keep it like this, times derivative of what I see here log b. Okay, so this is always positive. Always positive. Graph of x e to the x is always positive, no matter what power you give. Okay, it is sometimes less than 1, sometimes larger than 1, depending on the sign of this part. Okay, but we are not entering into that. It's always positive. So this thing is positive if b is larger than 1, negative if b is less than 1. Okay, so actually let me emphasize that we are only looking at positive things. If 0 less than b less than 1, and this is 0 if b equals 1. Okay, so that tells us what the function is doing. So here f is always increasing if b is larger than 1, decreasing if b is less than 1, and constantly the derivative is 0, so this is constant. Okay, constant if b equals 1. Well, if b equals 1, f of x is equal to 1 to the power some positive, some number. Okay, so that's equal to 1. Constant equal to 1. Okay, 1 to any power is 1. Okay, so that tells us what the graph is going to be. So the graph for several b, so the function you see is always positive. Okay, so this is always positive, e to the x. Okay, so I don't need the negative part on the y-axis, x, y. And when x is equal to 0, f of x is always 1. Okay, so note that f of 0 is 1 and f of x is always larger than 0. I make this observation. So all of them will pass through this point, 1. Okay, so this is the point 1. I don't know where to put this thing. This is 1. Okay, so when x equals 1, b equals 1, this is the function. This corresponds to b equals 1. If b is between 0 and 1, the graph will be something like this. So this is because the function is decreasing, and otherwise the function will be something like this. This is b greater than 1. Okay, so in the book you can see several of these things. As b increases, of course, the function becomes sharper, so it comes very close to here, suddenly increases. Okay. Okay. So we have this. We have, okay, so what is, so these things help us to find, we are looking at this, let me remind you why we are playing this game with different functions, and also next hour we'll look at other functions. We are trying to increase our repertoire of integration. Okay, so exponential function gives us some new integration formulas. Inverse trigonometric functions will give us new ones. So for this one, let us develop some rules. When you have an exponential function in the integrand, what do we do? Okay, so integration. Since we have d over dx of ex equal e to the x, we exploit this. So first of all, e to the x dx, as we know, is ex plus c. Now, of course, we change to b to the x. So what is d to the x, b to the x? So we know that we can write this exponentially, e to the x log b. So this is going to be itself times log b. Okay. So what does this tell me? If I want to integrate this, integrate b to the x dx, I have to write here a function whose derivative is equal to this. Okay? So the only function whose derivative is equal to this is the function itself up to a multiplicative constant. So I have to decide where I put that multiplicative constant. Okay? So if I take this function, if I take its derivative, I'll have this. I don't want this, so I divide it. Log b plus c. Okay. So for example, well, okay, let me skip these examples. Well, you love these numbers, so I don't know why you love these numbers, but let me play to the public. 2 to the x dx. So what is an antiderivative for this? Okay, so this one, 2 to the x over log 2 from 2 to 5. So you put in these numbers. Let's put these numbers to make you happy. Okay, log 2 minus 2 to the, well, here, since I did these calculations, let me change this because I did this calculation from 0. It's easier. 2 to the 0 log 2. And this is equal to 31 over log 2, and this is approximately 44.72 something. ln 2 is less than 1, okay, because this is log 2 base e. E is larger than 2. So ln 2 is e to the power 2 to the 2.7 to some power will give you 2. So that number must be less than 1. Okay, so log 2 is approximately 0.6 something. 0.7 actually, 6.9. So let's say 0.7. Okay, so this also gives us interesting things. So let me see how much time I have. Okay, so I can do this, and well, I can do the other one also. Okay, so let me mention this thing. So from the graph, now going back to the graph of f of x equals b to the power x. Here b is positive fixed, and x is anything. Okay. So its domain is R, and range is positive R, let's say positive, only positive real numbers, and always increasing. That is 1 to 1. So an inverse exists. Okay, so its inverse is denoted by y equals log to base b of x. Okay, if b is equal to e, its inverse is just log x. We don't write e here because it is understood. We decided that that's the natural base to write. Okay, so now what is the domain of the inverse and range of the inverse? Since this function takes these numbers here, its inverse takes these numbers here. So it just shifts R. Okay, so that that also fits to our expectation. Suppose b was e, suppose we were doing the usual thing. Logarithm takes only positive numbers and gives us everything from minus infinity to plus infinity. Okay, so we use the obvious rule, obvious obvious equations for general log. Okay, so we say y equals log to base b x if and only if, okay, b to the power y is equal to x. Okay, so that's the that's the definition. Okay, so the inverse of this function is this. Therefore, the inverse of this function is this. We do this so that we can understand how we take the derivatives. Okay, so what is the derivative of this? On this side, we know how to take derivatives because I changed this to the natural exponential. So let us see what we can do what we can do on this part. Okay, so here take log, the usual logarithm. So what does it say? Y log b equals log x or ln x. Okay. So here I have y equals log x over log b. Okay, so I suddenly obtained y equals something. So this thing is actually this thing. So that's why in general we don't open a new chapter for the logarithm with the new base, because logarithm with the new base is exactly the usual logarithm up to a multiplicative constant. Okay, so this was the first thing that was discovered when people discovered that the area under 1 over x gives you a logarithm. They discovered that if there is any other logarithm, it must be a constant multiple of the natural logarithm. And here we know exactly what that constant multiple is. Now, if you want the derivative of this, you see that the derivative is here. Then dy dx, here, when you look at this thing, you just take the derivative of this. This is 1 over x log b. These are natural logarithms. Okay? Okay, let's stop here. Next hour we continue from here.